This morning we're in a late model JK with a 6.2 LT. Pretty sure it's an L86, might be an LT1. You know the deal on that. This JK is on 40-inch tires. It's got a lot of stuff, but it's been done pretty good. I kind of like these visors. You know, back in the 70s and 80s, the Europeans used to use these tinted visors rather than solid ones, so you could get the shade and still see through them. This Jeep does have a lot of stuff like roll bar. This roll bar is bent, so it gives you a little bit more hood clearance, which I like. We have this electronic dash, and if we look at, this is the main page, you can see pretty much, well, everything is working. Let's shift gears here. If you look down there, all this information is on the, in fact, we're going to come back to the tap shift gate. You can see this has got a bump shifter in it. And one thing a lot of guys don't know is if I'm sitting here at a stop, and let's say when you first, okay, we're in drive, put it in bump shift gate. Let's say I want to climb a rock and I don't want it to shift out of third. I can bump shift up to third. Now the vehicle will take off, shift first, second, third, and stop. And it won't do anything until you either put it back into drive or downshift it or upshift it. So, well, let me qualify that. It will downshift on its own if it has to, but it won't upshift past that third gear. So if we look at the data here, we got coolant temp. You can see we got oil temp, oil pressure, gearbox is transmission temp. We can come over to this page here, which is the four-wheel drive stuff, media, which is whatever you're playing, I guess. This is navigation, maintenance, settings. I'm assuming we don't have tire pressure sensors in these 40-inch tires, so they're reading max 239 psi. And then some of the vehicle information, like a lot of you guys don't know that you can set your JK to automatically lock the doors once you get lock the doors once you get going a certain miles per hour. Now all this stuff is available on the can, and every vehicle has it, even the early JKs, but it's just how it's displayed that is the difference. So let's go back to the main page, and I thought we'd talk a little bit about engine performance, because I think engine performance is something that's not really well understood, and this applies to pretty much everything, meaning it doesn't matter if you have a 4-cylinder turbo or a V8, the basics of engine performance are all pretty much the same. Really, the basics of internal combustion engines, or ICE engines, haven't changed for well over 100 years. I just had a 1929 Model A that I helped adjust the brakes on. They were mechanical and get the engine running right. And that engine had mechanical controls for timing and mixture. So right on the steering wheel, you had little dials. By the way, guys, cruising up the Parkway is effortless with this LT62, even with these 40s and this heavy Jeep. I don't really like that small tachometer, but we're going, looks to be about 1700 RPM. Let's see if we can switch pages here and make it bigger. Yeah, about 1700. In any event, this Model A had a separate lever for timing and mixture. And you could mechanically lean the motor out to get better economy. In the morning when you started it, you could richen it up. You could back the timing off when you're under a load. When you weren't under a load, you can increase the timing. I found it interesting how much control you actually had over engine performance. But it was all manually input, which means the driver had to know what he's doing. So if you think about right after the turn of the last century, 1913, 1914, you're driving a Packard, or even just a Ford Model T, or in the 20s a Model A. You really had to have special knowledge to drive these vehicles properly. Of course, a lot of people didn't have special knowledge, so they just drove them however they could make it run. But for somebody who understands the principles of mixture and timing and temperatures and load, they can get the most out of that vehicle by manually adjusting everything. Now, you couldn't get quite as much control as we can today, because today, like with fuel injection, sequential fuel injection, you can actually control the spark and fuel in each individual cylinder. Back then, they were running carburetors, so the overall mixture, and it had to go through an intake manifold, and of course there were inefficiencies in the exhaust, as far as the runner lengths and all that. So you had to pretty much treat the engine as a whole rather than individual cylinders. But I found out with that Model A that if I concentrated on all the basics and I adjusted everything for maximum economy or maximum performance, you could really get a lot more out of the vehicle. It did take a lot more work on the driver's part, and that's where today's engines differ. With computer control, the driver pretty much hits the key or pushes a button and they're on their way, and they don't have to change anything, and they're getting great power and good economy. But the basics of engine performance are crucial. If you want to be a mechanic, if you want to be a diagnostic technician, if you want to be an emissions inspector. And I remember back when I took the state tests for emissions, and most guys don't pass it. I think it was at the time 88 to 90% of the people that challenged the state G2 test here in Nevada failed it. Most guys got their licenses through an L1, ASCs, etc., or military. But I challenged the test, I passed it the first time. Some of the answers could be very elusive. Things like, if you had a weak ground over here, what effect is that going to have over here at the ECM? And then you have to try to calculate what would happen with that power circuit if you had a weak ground somewhere else. Or what makes a good conductor versus a good insulator. We all think dielectric grease makes good contact, and it's actually an insulator, and it's meant to keep moisture and debris away from the contacts. It's not a conductor, it's an insulator. Failure modes. When I took the test, this is right about the time that Onboard Diagnostics 2 was being implemented, and prior to Onboard Diagnostics 2, a lot of vehicles that would have a failure, let's say in the MAP sensor, that's the manifold absolute pressure sensor, would just go full fat. Because remember, failure modes always tried to resort to safety, so you could drive home, so the vehicle wouldn't stall on the highway, whatever. And when you floor it, and a lot of guys don't know this is true since the late 1960s, when you floor it, emissions devices in general are bypassed. And that doesn't matter if it's an EGR valve or an air system, they do their best to bypass the emission system to give you the maximum performance. So a common failure in the early throttle bodies, like let's say the K motors in the Chevys, and Ford did the same thing, was if the MAF sensor failed, the engine would go full rich. Well, that's something you didn't want to do for the environment. So there would be questions related to what would happen if a MAF sensor would fail in this particular vehicle. And they usually picked out failures that were quite common out there, and guys with experience would know the answer. And that's something I can convey. Over my years in automotive, and that's going on about 40, I've had lots and lots of people work for me. And when they come out of these colleges, automotive colleges, we've had guys from Wyotech and Arizona, whatever. In fact, I had one employee that graduated first out of 320 graduates. And when she, yes, it was a girl, came to work for me, she was book smart. She knew pretty much everything. But when it came to actual experience and hands-on, she knew nothing. We had a GM V6 come in, Illumina or something, and it was making a strange noise, and it was running really rough. Well, those early V6s ran the crank sensor inside the harmonic balancer in the back. And, well, when the harmonic balancer came apart or a belt would shred, it would contaminate that signal and the engine would start running rough or it would just die. So when the vehicle pulled in, I knew within a few seconds what was wrong with it. But she was going through all of her books and manuals and charts and everything else. And you gotta remember, back then, we didn't have as much computer-aided diagnostic. So some of the codes weren't as accurate or as easy as they are today, especially prior to OBD2. Because prior to OBD2, yes, we did have OBD1, but every manufacturer was pretty much on its own. So Toyota had its own data link connector. Honda had its own data link connector, had its own language, had its own code charts. Honda was really bad because they had multiple data link connectors, and guys say, well, you can't have more than one. Yes, you can have many. They had data link connectors for the ABS system, for the engine performance system, for the chassis systems. Chryslers in the early 90s were pretty advanced when they hooked up with Mitsubishi, and they went to a CAN bus, an internal CAN bus, and it was extremely fast. It was not well understood. Crazy things would happen, like your temp gauge would freak out, and the problem was in the ABS module. And I learned the hard way with the early CAN systems, the diagnostics, if you have a bad temperature gauge, who's going to think that you have a problem in the ABS module? But some of these serial CAN networks would just transfer corruption from one module to another. So getting back to just common sense, having the experience of seeing the harmonic balancers fall apart over and over and over, I could diagnose it without even opening the hood. But after some time diagnosing, a book smart person could probably come to the same conclusion. And that's the difference between being book smart and experience. And a good diagnostic technician needs to have both. They need to have experience and they need to have the book smarts. Being able to read a scanner or a pattern. Before we had these scanners that we have today with plug and play waveforms and all this, we had to figure stuff out the hard way. We had to hook up a secondary scope, like if we had a miss. And somebody who could read a secondary pattern could tell if you had a slip timing chain, could tell if you had a weak cylinder, could tell if the cam was going flat. That knowledge no longer exists. It's just like mathematics today, where kids have calculators, where they can't do logarithms and other mathematic calculations because they're so dependent on technology. We even had amperage waveforms where we could hook up to, let's say, the starter motor and read the amperage while cranking, because remember, an engine is basically an air pump, and we know all 8 cylinders in the V8 should be plus or minus a few percent of each other. I think the actual standard is about 15, but I don't like to see them that far apart. And when you crank the engine, the amount of energy required to crank the engine is going to change based on which cylinder is under compression. So you could read that and check if there was a mechanical problem. And one of the questions on the Nevada G2 test here was, what is the most efficient way to check the mechanical condition of an engine? So they gave you options: a vacuum gauge, a leak down test, tear down, etc. Most guys would say a leak down test, because that is very accurate. You pressurize the cylinder, and then you watch how fast it leaks down. You actually feed air into it, and you try to hold a constant, let's say 100 psi, and if that engine, well, one, it has to be on top dead center, and the valves have to be closed. But if that engine has anything that's not sealing, whether it's a piston ring, a cracked piston, a valve seat, etc., even a guide, that's going to show up in the leak down test, and it's a pretty accurate test to determine where the mechanical problem is. But that's not what the question said. The question said, what is the most efficient way? And of course, it's a vacuum gauge, because you plug a vacuum gauge in, and if you're a mechanic and you can read a vacuum waveform, if the vacuum is low all the way across the board, or even high all the way across the board, you probably know that you have a valve timing issue. If you have a needle that's not steady, it's ticking, well, you could have low compression, you could have a bad valve, and a mechanic that knows what he's doing can look at that vacuum gauge and pretty much hone down where what the problem is, or what direction to go in to determine what the problem is. In fact, we had a JK recently come in the shop that was at another shop, and the JK went out and got custom tuning done. When we pulled the tune out, all the safety stuff had been turned off. The rev limiter had been set up to the moon. The performance enrichment was maxed out. It was obviously a performance tune. Now, the thing did run hard, but it had an intermittent miss, and it was throwing a P300. So we called the customer and said most likely what happened was somebody removed all the safety features. Now, this was an AFM engine, or an active fuel management engine, and everybody first tries to blame the AFM components, whether it's the lifter or the solenoid, but that wasn't the problem. The engine had been revved really high, and the number 3 intake valve was not seating. Now, I don't think it was bent. We sent it to the machine shop, but it wasn't seating. I think the guide was damaged from over revving it, and the valve couldn't seat. Because remember, these heads are aluminum and they have pressed in hardened guides. So before we could go any further, we had to repair the mechanical component of the engine, and that's something that's missing today. When most shops get a vehicle in, they hook a scanner up. First thing they look for is a misfire or a code that's going to tell them what's wrong. Then they're going to look that code up on the computer, Mitchell, AllData, GDS, whatever, YTech, and hope that that's just going to tell them what the problem is. But the thing is you might have a mechanical problem and you might be trying to fix it with a scanner, and you can't. And that's exactly what happened to this vehicle. It had been to a couple of other shops, and the customer was given the runaround, and oh, your TIPM is bad, and you got a bad computer. And of course, the problem all along was just a mechanical failure because of a bad tune. So that's where experience comes in, and knowledge. And I can say, having been working as a mechanic since the early 1980s, and even doing engine conversions since the late 1970s, I've seen a lot of crap. I remember I had a BMW come to us from, this is back when we were in Los Angeles, and a lot of Beamers there, and it had been to all the shops, it had been to the dealer, and no one could figure out why this BMW would stall in a turn. It was a 320 something, I don't know what their numbers are, but it was a 6-cylinder BMW. BMWs were not the easiest vehicles to diagnose because they had odd connectors, which most shops didn't have. They had odd protocols, and even when you did get the data stream, it didn't really help you that much. What it turned out to be was moisture in the airflow sensor, and when you went around a turn, this water would puddle on one side of the sensor and short it out or change the reading. So the solution was to replace the sensor. Now, the early Datsuns and Porsches and a lot of the Bosch stuff did run a air vane meter, which a MAF sensor or a mass airflow sensor measures the incoming air by warming up a little sensor ball. It's like a resistor, and tries to hold a constant temperature. So as you go faster and faster, more air goes over that sensor and cools it down. So they got to pump more amperage into it to keep up. So by measuring the amount of current going into that sensor, you can effectively measure the airflow. The early GM MAF sensors were awesome. In the late 1980s, the Corvettes and the Camaros with the tune ports, I had an 89, I think it was, 88 Corvette that had the MAF sensor system. Now, they did drop the MAF sensor system like a lot of manufacturers. In fact, Chrysler in general still doesn't run them. But having actual airflow tables can help you a lot because it can kind of tell you what the humidity and the air density is. So if you go up and down in altitude, the MAF sensor can definitely add some drivability, and overall the drivability with a properly working MAF is unmatched in my opinion. Now, racers are going to argue, yes, but they're more delicate and more sensitive to airflow, which is true, but rather than using a MAF lookup table like speed density where it's just looking at engine RPM and intake vacuum, it can be much more precise. So let's say I'm here in Vegas at 2,000 feet and I drive up to Utah at 6,000 or 7,000 feet. The air density change is definitely a variable you want to know about. On the earlier speed density systems, and Chrysler to this day I think still has this issue, if the air density changes too much because of altitude, it's going to change the fuel output. And guys with the Penstars used to complain, hey, you know, I'm in Colorado, I went from 2,000 to 8,000 feet and it started running really weird and lean, but then I restarted it and it worked fine again. Because the manufacturer would recommend every 3,000 or 4,000 feet, stop, and this is true with the feedback carburetors too, stop, cycle the key, because when you turn the key on, the baro sensor, which is the atmospheric sensor, takes a altitude reading or a barometric reading, and then it uses that as its base calculation. But having an airflow meter, and especially now with the LTs, you have an intake temp sensor, so you know what the temperature of the air is. You have a humidity sensor, so you know the water content in the air. You have an airflow meter, so you know the speed of the air or the volume of air coming through. And with all that information, you can just make better decisions. The flip side is if something goes wrong with the MAF sensor, like you have an air leak, your air filter falls off, then it's going to run really crappy versus a speed density. But when it's working right, there's nothing else like it. And some of the economy numbers I get with these MAF systems are great. I'm rambling right now, but this is probably stuff you're not going to hear in a lot of places because I was around a long time ago. But in the late 80s, the MAF sensor, the mass airflow sensor, the GM V8s were just awesome. I was getting 22, 23 miles to the gallon in my 350 Corvette. It was the, I don't know what generation it was. You know that after the Stingray went to that new generation in 84, I think it was. So in 89 with a tune port MAF sensor, not only was it quick, but I could get really good economy. And you guys know that I used to work with Chris Jacobs, and it was all coming together. The spark knock, the fuel delivery, airflow calculations, it was all kind of coming together then in the late 1980s. And in the 1990s, we all really benefited because the operating systems simplified the engines greatly. You go look at a mid-90s fuel-injected, let's say V6 Lumina versus a mid-80s, and that mass of hoses and emission components and all the other stuff is gone. And these port fuel-injected engines were just running phenomenal. But they did have a problem with the early MAF systems, and this is kind of why a lot of manufacturers shy away from it. It's such a sensitive sensor that if somebody oils their filter or over-oils it and contaminates that sensor, or dirt gets in because you're off-road, you're not running a proper air filter, that's going to change the airflow tables and your engine's not going to run right. So GM came up with a brilliant idea, which I'm sure they wish they hadn't, of the MAF burn-off. And they had this relay that when you shut the car off, it would pump a lot of amperage through the sensor bulb. That would make it burn red hot and burn off any contamination, hopefully, which it pretty much did. But the system was very troublesome. it had a lot of amperage going through it, and we saw the relays and wires get damaged, and GM finally said screw it and went to a speed density system in the early 90s, and you could really tell the difference. Throttle response wasn't as crisp, mileage wasn't as good in my opinion. It just wasn't as good of a setup, but for a production vehicle, that's what they had to deal with. In the mid 1990s, the same problem happened across the GM lineup, because especially like the midline and low line cars, the Grand Prix and things, people would never maintain them. They would never change their air filters, their rubber boots would get tears in them, and the mass sensor proved to be unreliable in vehicles that weren't maintained. So GM had an update to eliminate the mass sensor. It was a calibration update, and you just essentially removed it or unplugged it, and then the vehicle would run in speed density, and they just didn't run as good. And in my opinion, the same thing holds true today. Now, technology has made the mass sensors a lot more reliable. That doesn't mean you can have air leaks, and guys don't know, but the crankcase runs through the PCV system, or the positive crankcase ventilation system, and that does affect the airflow going into the engine, because the scavenge tube goes between the mass sensor and the engine, so the mass sensor can read the airflow coming back up through the crankcase. So even something as simple as a dipstick tube, which is sealed, that has an O-ring, or an oil cap that the cap is missing or the O-ring is damaged, can cause the MAF system to not work the way it's supposed to. But today, I find the MAF system to be pretty reliable. They've made changes to the sensors so they're less susceptible to contamination. There's failure modes, and some of you guys might see P0101, 102, which is airflow irrationality. One of them is circuit, one of them is irrationality. And it can actually diagnose itself and say, hey, my fuel trims, if you look at the fuel trims and they're swinging wildly from plus to minus, you probably got a problem in the MAF system. Now, it could be a bad calibration, like a guy takes a stock 6.2 calibration, then he cams the engine, and he doesn't change that MAF airflow to match the new engine, you're going to have a problem there. But if you run a stock vehicle like we do, stock engine, stock MAF, stock everything, then probably you have either contamination or an airflow leak or something along those lines. When the MAF system is working the way it's intended, it's going to maximize economy, it's going to maximize drivability, your throttle response, everything is just going to be better. Now, the LTs do run very sophisticated MAF sensors. In the older days, the air intake temp sensor was mounted independently of the MAF sensor, but they figured they could save a little bit of money by incorporating it into the MAF sensor. And then when the LT came out, not much changed. But when they added the humidity sensor, they're pushing 9 wires on that sensor. So what GM did, just like they did with some of the other sensors, like the fuel pressure sensor, they designed that sensor to work off a serial network. So now we're not just getting one signal over one wire, you're getting multiple signals over the same wire. And that technology has been around for a while, you know, a lot of the LIN bus or interior stuff. However, the MAF sensor is an extremely fast sensor. The feedback from it, one of the reasons they don't use 5 volts, and I'm getting into more technical stuff here, but most of the sensors, whether it's a MAP sensor, a fuel tank pressure sensor, EVAP, all that stuff is pretty much run off of 5 volts. But because the MAF sensor runs so fast, they made it a digital sensor, so it's not analog. Analog sensors essentially have a 5 volt reference, that's the output. They have a low reference. Low reference is ground supplied by the computer, and that way it's like a hammer and an anvil. The low reference is the anvil, you have something to work against. If you had an anvil made out of foam, it wouldn't be as good as one made out of steel. And that is what happened with the early computer systems when you were grounding everything off the battery and you put an electronic control unit or ECU in, and there, let's say, was a half a volt drop between the battery ground and the ECU ground. So now you got 500 millivolt drop. You got an O2 sensor working at 0 to 1000 millivolts. You can see the problem. So what they did is they put the ground or the low reference internal in the ECU so it could get proper feedback based on its own internal ground. But the MAF sensor is different. It had to work fast. As I remember, there were some early analog MAF sensors, but pretty much over time they went to digital, and digital measures the frequency. So a modern MAF sensor might be idling at 2000 hertz, and it might go up to 10,000 plus 15,000 hertz at wide open throttle with a lot of airflow. So you have a lot of definition there. GM also used solid 12 volt and ground on the MAF sensor, because remember, now we have a digital signal. So we don't need feedback to the computer in an analog fashion. And I know this is getting confusing, but having a digital signal means it's just looking at the frequency. It's not looking at an analog feedback. So by giving it full 12 volt power or system voltage and ground means that mass sensor can run at high speed and sense changes instantly as fast as you move the throttle. And when they are working the way they should be working, they really are pretty amazing. Let's take a look at this Jeep while we're changing the drone battery. He's got a hinge mounted spare tire, which seems to actually work pretty good. Usually these aren't this stable because these tires are heavy. They can weigh up to 200 pounds. We've got Method bead locks, Poison Spider armor, these tree catcher things, this hood, which is really popular. I've never really been a big fan of it, but it's starting to grow on me. It looks like this guy's been to a lot of places. Typical synthetic winch. This bumper's not too bad, not blocking too much air. Of course, we're not having any problem with overheating right now because it's winter. I'd probably relocate that LED light, but it's doing pretty good. We got TerraFlex Falcon shocks, which are adjustable, and yeah, TerraFlex long arms. It's a really nice driving Jeep. Let's open the hood. I haven't looked under the hood of this one yet. All right, so this is a typical 6.2 LT. I'm not sure if it's an LD6 or an LT1. Typical Motec battery tray, coolant bottle. I don't know, that's the Switch Pros it looks like. Yep, Switch Pros. And they cantilevered it off the firewall. Now look how short those wires are between the Switch Pros and the battery. And notice the battery has three, kind of a bus. It's only 3 studs. Better than one, because we see guys gang up all sorts of stuff on one stud, and that's not good. But running the Switch Pros here, I think you can see how small it is a lot more efficient than running it over there and running those cables across the firewall. That's a short cable and it's really heavy gauge, so I don't think I'll have any problem. Looks like what he did was he just put his own bus bar in this off the Switch Pro to make hookup easier. This Jeep, I guess it does have a lot of stuff on it, but it was done clean. The customer did a good job, and that's what we like to see. This is a typical Pennstar transmission cooler, which works well. We got our aluminum AC condenser behind that, and this is not a Mopar AC condenser. It's a aftermarket one. We find that the aluminum's softer, and there's a little bit more spacing in the fins. I don't know if you can see that. Mopar uses a real high efficiency fin, and dust and dirt goes in there and plugs it up, and then it just restricts airflow. And then of course our quad header radiator, all aluminum, custom built for this application. You can see we got a steam port over here, which is really short. We are using AC Delco caps now, and here it is if you want to get one for yours. We were using Stant, but Stant got bought out by Motorrad, and now they're using Motorrad, and we've never been a big fan. This LT1 or L86 pulls this heavy JK with ease. It's just amazing. It feels like it's 2,000 pounds lighter than it is. So let's get back on the trail.